Hello, good afternoon, everyone. Am I audible? City, New Delhi, and MTech in Signal Processing from Netaji Subhas Institute of Technology, New Delhi. He has worked as postdoctoral fellow at Alberta University, Canada, where he worked on where he worked on various projects of national importance, including development of various systems for Indian and foreign defense forces. He has been awarded research and development Singh. Sir, please.
Thank you, ma'am. Thanks for the nice introduction. So without wasting time, I'll straight away head to the presentation. So let me share the screens. I hope the presentation is visible to all. Okay. So basically, we will be talking about the application of artificial intelligence in the field of medical image analysis and how we perform medical diagnosis with the help of different AI techniques, specifically machine learning and deep learning. So if we talk about the agenda of this talk, we will have quick introduction of deep learning. I won't devote much of the time on the basics of deep learning. I'm sure other instructors in this FDP must have thrown some light on the basics of deep learning. Then we will talk about the footfall of different deep learning algorithms in medical applications and medical diagnosis. We will discuss the practical aspects. How do we build the models? What are different challenges associated while we are training and building the models? How do we test and evaluate the trained models? What are different public data sets which you can use in your research? All right. And in the last, we'll have a small demonstration where we will see how COVID-19 can be detected from the chest X-ray images. So we'll have a demonstration for you on Google Colab. The historical aspect, what is the basic difference between AI, ML and DL? I hope since the theme of this particular FTP is in line with these three terminologies, I hope you must be aware of these terminologies, but still I would like to clarify on these three terms: artificial intelligence, machine learning, deep learning. Broadly speaking, AI, the term AI was coined somewhere in 1950s and 60s, and the idea was basically to develop the intelligence in the machines so that the machine can or the computers can mimic the human behavior. The term itself says that we are generating the intelligence artificially. But in my opinion, there is nothing artificial intelligence kind of thing. It's all the human intelligence which we are transferring to the machines or the computers. Let me give you a small example of it. In the traditional uh, artificial intelligence methods, basically, one of the popular were the rule engines. The software programs were written in such a way that whatever rule engines a human applies in daily life can be transferred in the form of a software code on your computers. Suppose we have to identify different kind of routes. So how does a human identify those routes? I mean, suppose we have to differentiate between uh, a apple and a banana. So maybe color is one of the option. The shape is the another feature which we consider while differentiating between these two fruits. So can we develop a software where we can write a small program and define a rule engine in such a way that if the color of the fruit is yellow, then it's a banana. If the color of the fruit is red, then it's an apple. Maybe we can have a nested loop where we can consider the shapes as well. So this was the historical idea of artificial intelligence, where we are uh, enabling the computers so that they can perform the activities which a human can perform. But there were certain limitations to it. We cannot transfer the complete knowledge of a human in terms of a software program. Every time we have to change that software program. There are certain limitations to it. That gave birth to the machine learning concept. It said that we should not program the computer or the machine explicitly. Rather, the machine should have that ability itself that it can learn from the examples. What is the idea? We will provide the image of different fruits and tell the computer or the machine that this particular image belongs to this fruit. We won't write those rule engines or something like that. In machine learning, the term itself says that machine will learn from examples. It will extract some kind of features and then build the intelligence itself which a human possesses. The third part is the deep learning, which is first of machine learning, and it is basically based on the neural networks. So the term deep means you have large number of layers. The network is very deep. Usually the artificial neural network have three layers: one input layer, one hidden layer, and an output layer. However, in the case of deep learning, we have n number of hidden layers. That's why the network is deep, and that is the reason we call it deep learning. The basic difference between the traditional machine learning and the deep learning is there was a dedicated step involved in machine learning, that is the feature extraction part. However, in the case of deep learning, it's a complete pipeline which performs the feature extraction as well as the classification part. So what is basically the deep learning? It extracts the data from the extract meaningful information or the patterns from the underlying data. Deep learning is inspired by the human brain. The way information is processed in a hierarchical manner by our human brain, the concept of deep learning is also similar. We have hierarchy of multiple layers, and each layer is capable of processing those information and extracting some meaningful information from the underlying data. That is nothing but the representation of the data, whether it is a image or video data, or the textual data, or any other kind of data. Why deep learning has become popular in recent times? Now we should not say that it's a recent time, it's close to 1 decade where deep learning has become popular. Somewhere in 2012, it started gaining popularity. Thanks to the availability of high-end computing resources like graphical processing units, GPUs, the open source softwares like TensorFlow, Caffe, Keras, PyTorch, and abundance of data, public data available for experimentation. That is the reason deep learning has become popular in recent times. So as I was telling you, the conventional machine learning pipeline has a dedicated feature extraction step. However, in the case of deep learning, that feature learning or feature extraction part is the constituent of the model itself. We do not have a dedicated feature extraction. Let me tell you, like, what was the basic problem with machine learning? We have to extract features for different type of domains. Suppose we are building a model for facial recognition. So we have to extract features from the facial images. Now, the limitation of this model is we cannot transfer this model on a different domain. Suppose tomorrow I want to make a fingerprint recognition model. So I would have to change the feature extraction step. This feature extraction is not generalized for across the domains or across different type of. So that limitation of traditional or conventional machine learning is solved by deep learning, and how deep learning is mainly it involves the learning of the representation of the data. Okay, so basically, as I was telling you, there is a hierarchical processing of the information. The way our human brain perceives different scenes. We also have different layers of information processing in our brain. Similarly, deep learning, the different layers of neural networks or deep neural networks learns the meaningful information from the data. The starting of the layers will learn the low-level features. As we go deeper into the network, we will be able to extract the mid-level features and the high-level features, like the facial structures in case of face recognition models. We also call the traditional machine learning the features computed in the traditional machine learning pipeline as hand engineered or handcrafted features, and they are basically very time consuming and not scalable in practice. Just give me a moment. So one of the popular architecture of deep learning is convolutional neural network, and which is very popular and shown very promising results in computer vision field. So the convolutional neural network consists of different type of layers, and each layer has its own working, and significance. As we have convolution layer, so convolution layer, the name itself interprets it, that we perform some kind of convolution operation on the input data. So the idea here is to apply different kind of filters or masks to extract the information from the input image. So now onwards, I'll be discussing from the computer vision perspective or the medical imaging perspective. So we are only considering the image or the video data here. So as you can see in this diagram, the convolution layer involves convolving different type of filters for extracting different kind of information from the input image. As you must be aware of, we have a different type of filters in image processing, the edge detection filters, the Sobel operators. So those type of filters are applied here on the image so that maybe we can extract the edges and lines. And basically those edges, lines and corners constitutes the distinguishable information in an image. Why do we need the distinguishable information? Suppose we want to differentiate between two faces. We want to build a model for face recognition, or we want to train a model for diagnosis of COVID-19 using chest X-ray. So we have to basically extract those kind of features, those kind of distinguishable features which are easily able to differentiate between a normal patient and a COVID-19 patient. That's why the idea here is to extract distinguishable features, unique features. And we need not to worry about that. This complete pipeline of convolutional neural network is capable of learning those features from the input image. Okay, so we have convolution layer, then we have activation layer, that is rectified linear unit. It is an activation layer and it brings the non-linearity into the pipeline. Then we have pooling layer. Pooling layer is responsible for the dimensionality reduction of the input data. As you can see, the cuboid has, it's of reduced size. Since nowadays the input data are of very high dimension, and processing this complete input image of high dimension requires a very high-end computing system. So the idea here is, with the pooling layer, we are reducing the dimension of this input data without losing the information, without losing the spatial integrity of the image. And in the last, we have certain layers which performs the classification tasks. So softmax is a classifier, probabilistic based classifier, which assigns a particular class based on the score of that particular class. You can see the example here, as the input image is given as the flower image is given as input. And the starting layers are responsible for extracting the edges and lines, and slowly this information is processed by different hierarchy of the layers, and the small shapes are being constituted, and in final stage of this CNN we are able to constitute the objects. And finally the classification is being performed on the representation constituted by the CNN. So now, from the basics, let's switch to our main theme of this presentation. The story behind, the story started somewhere in 1970s, and Dr. Lodwick was the first one to apply any kind of, he started the computer-aided radiology. Before this, everything was manual. So he was the first one, I mean, his group was the first one to propose that these medical modalities can be transformed into digital domain, and once they are in a digital domain, they can be read by the computers, and we can implement some intelligent algorithms on those digital images. So for this particular work, he received the nomination for Nobel Prize. So basically, he worked in the field of image modeling and the computer diagnosis of bone tumor with the help of computer-aided radiology. So that was the inception of, I would say, computer-based diagnosis of medical imaging. That was the start of medical image analysis using your computers. As far as the current scenario is considered, the latest AI technique, that is deep learning, is having the presence in each and every aspect of medical domain. You will not be surprised by knowing that deep learning is helping in the development of new antibiotics. The discovery of new antibiotic is very complex subject, and most of the times the researchers end up in discovering the same antibiotic again and again. So people are applying deep learning for discovery of new antibiotics. The major companies like Google, Facebook, they are investing too much in applying these AI techniques in the field of medical diagnosis. Recently, researchers are able to diagnose COVID-19 from the chest X-ray image of the patients. As you are aware, the RT-PCR test has certain limitations, and the diagnosis based on the chest X-ray of the patient gives you an advantage over RT-PCR based tests. There are certain use cases of deep learning in the medical field. There is a startup called Analytic. It has developed a device, and it has surpassed the combined abilities of a group of expert radiologists in detecting the lung cancer in the computed tomography images. So in some of the cases, these deep learning powered medical diagnosis tools has surpassed the performance of the doctors and the radiologist. Of course, these deep learning models are trained with the help of the knowledge of these radiologists and doctors, but once they are trained and provided ample amount of data, the performance is very high. Similarly, Google has, Google's lymph node assistant, they call it Lina. It is able to detect breast cancer from the pathology images, and that too with 99% of success rate. However, in this particular domain, human doctors have the accuracy of somewhere around 38%. So the list is endless. There are n number of applications of AI, machine learning, and deep learning in the field of medical image analysis. So let's see how this magic happens. So let's take an example of COVID-19 detection. So basically, we will provide a chest X-ray image to the model. This model will be trained, and this model will be able to give us score on these particular classes. So we have suppose 3 classes, whether this chest X-ray belong to COVID-19 category or a normal pneumonia or a healthy patient. Similarly, another medical domain where AI or deep learning has been extensively utilized is detection of diabetic retinopathy. The diabetic patients have a tendency of losing their eyesight. Sometimes it can lead to the vision loss. How does it happen? Basically, the diabetes affects the blood vessels of the retina and they are damaged. And in the worst cases, a diabetic patient can lose the eyesight. So basically, for detecting diabetic retinopathy, we have a medical modality called retinal fundus image that is captured by a special kind of device. This retinal fundus image is provided to the model or algorithm, the AI or deep learning model algorithm. This particular model will give us output in terms of whether this fundus image belongs to normal category or damaged category. Another area, and in fact one of the most popular medical modality, is the MRI. As you are aware, the MRI is very complex data. It has certain layers, and each layer has certain significance. The amount of data provided in a MRI is very huge. So in the case of brain contains different type of fluids, and based on the density of these fluids, different diseases are diagnosed. Based on the structure of your brain, different diseases are diagnosed, whether it is Parkinson, Alzheimer. So the AI based models or deep learning based models helps in automatic segmentation of MRI images. Another test case is detection of breast cancer, and the medical modality which is being used is histopathology images. So these are basically the microscopic images of your blood. So the model basically takes these histopathology images as input, and it detects whether this histopathology image is benign or malignant, whether they have some kind of symptom or cancerous symptoms in these images or not. And we have other applications too, like prediction of medical events. You must be aware of the epileptic seizure. So the easy modality of a patient can be analyzed to detect the seizure. People are also developing models for detection of cardiac arrest. Drug discovery, analysis of electronic health record, automated medical report generation, that is one of the emerging field where by seeing the medical modality image, a automatic report can be generated, and many more. So let's come back to our original discussion. like how do we detect COVID-19 from chest X-rays? Suppose we have certain examples. We have a collection of chest X-ray images of the patients who came at a lab for the tests. And we know that these particular chest X-rays belong to the patients who were diagnosed COVID-19. And we have another data available for the healthy patients. So given this data, a radiologist will be able to diagnose whenever a new patient comes by just seeing that chest X-ray. It can correlate with the examples available with the radiologist and identify whether the new patient belong to which category, whether it is COVID-19 or normal. Similarly, these AI or deep learning models also work. We provide these labeled examples for training the model, and whenever there is a new chest X-ray available, the model should be able to identify which class it belongs to. So these models also works the way a human work. We provide examples, and based on those examples, these models learn. And once they are trained enough, then they will be able to identify or diagnose a new chest X-ray image. So whenever a new chest X-ray image is provided, the model should be able to identify whether it belongs to normal category or COVID category. So now our discussion reaches to the training of the models or building the models. How do we train these models? So basically we provide thousands of chest X-ray images of both the categories. Here we are taking only two classes, COVID-19 or normal. And these algorithms models learn from these examples. We call it labeled example. I'm here talking about the supervised machine learning, where we are providing the labels corresponding to the different categories. These algorithms models can be deep learning models, convolutional neural network model, or any artificial neural network, and many more. So the idea of learning here is, for each of the chest X-ray image in the training set will have a corresponding label. It is the task of the algorithm or the model to learn those representation or the features from these X-ray images which are helping them to differentiate between these two classes. So the features which this model or algorithm will extract will help this model to differentiate between these two classes. How does it happen? So suppose for the COVID category, the desired label is suppose 1, and for the normal category, the desired label is suppose 0. So in the starting, we compute the prediction probabilities and see how close they are to the desired label and compute the errors. And the whole idea here is to minimize or to reduce this loss or error very close to 0. Once this error becomes close to 0, these prediction probabilities or the desired labels will be accurate one. So initially we will provide some examples. There will be error and that will be very high. We backpropagate that error to this model in such a way that the parameters or the weights of this model are adjusted, and in the next iteration this error will be reduced. And slowly, it's an iterative process. After certain number of iterations, this error will approach towards 0. So this is some kind of optimization problem where, or optimization or minimizing problem where we are minimizing the error by adjusting the parameters of these algorithms and models. So we formulate some kind of cost function or a objective function and try to minimize that cost function or the objective function. So slowly after iterations, this error will be approaching towards 0, and the desired labels will be, these labels will be close to the desired labels. In the case of histopathology images, where we earlier discussed about the breast cancer detection, so these histopathology images are of very high resolution. Directly applying these models on these high resolution histopathology images requires a very high-end computing device. So the idea is we can sample patches from this complete image and consider this patch as a new image and provide this as an input to the model or maybe the convolutional neural network. So basically we are assigning the labels to these patches instead of this complete image. And we are treating these patches as a newer image. So that is also possible. Instead of giving a very high resolution and image as an input, we can sample patches. These are some of the popular convolutional neural network architectures which are being extensively used in the field of medical image analysis, like Inception V3, ResNet 334, DenseNet, SqueezeNet. So they have their own uniqueness, and different type of architectures have different kind of results on different modalities. So it's up to you. How do you want to proceed? What kind of architecture you want to choose? Nowadays, you have pre-built or predefined architectures available. Pre-trained architectures are also available on certain data sets. You can apply certain kind of transfer learning approach and use these readily available CNN architectures. So let's revisit it again, and how does the CNN do the task of this medical image analysis. So we provide a input image. In this example, we have the MRI image. Different type of filters are applied in the convolution layer. So convolution and activation layers are combined here. Then the pooling layer, again the hierarchy of different type of layers, and finally we have fully connected. It is connected with each and every node of the previous layer. And basically the idea here is the fully connected layer, the last fully connected layer provides the score for each of the category or the prediction probability for each of the category. Then we apply the softmax classifier and it assigns a particular class which have highest probability. So in build, basic challenge or specifically in the field of medical domain, we have a problem of size of the data set. Specifically, the minority class, I mean, the examples for the diseased class are very less. Let's take the example, suppose we are detecting COVID-19 from chest X-ray images. So in the starting, we might be having very less number of chest X-ray images for the COVID-19 patients. So that problem has to be resolved first before training your models. And we have a solution available in convolutional neural networks. One is transfer learning or fine-tuning of pre-trained CNNs. How does it happens? So the term itself says transfer learning. So we are transferring the learning of one domain to another domain. Since we don't have ample amount of training images of medical modality, what we can do is we can take a pre-trained convolutional neural network on another domain where we have abundance of images available. Then take this pre-trained convolutional neural network and fine-tune it on the data set of medical modality. Let me tell you why it is efficient, how it can perform. I mean, a model trained on different type of images, how it can work on the images of medical modalities. As I was telling you, the convolutional neural network have hierarchy of layers. The initial layers are responsible for extracting edges, lines, and corners. So whether it's an image of cat and dog or it's a chest X-ray image, the filters involved in extracting lines and edges will remain same. The methodology of extracting edges and lines in a particular image won't change. That is the reason we need not to train the starting layers for medical modalities specifically. If those starting layers are trained on a different data set, it will work fine. And the fine tuning here means we are only retraining the last layers. So maybe the convolutional neural network earlier might have been trained for the classification of 10 classes, and in our medical modality problem, we might be having only 2 or 3 classes. So basically those layers has to retrained, and those can be retrained on a very small amount of data. And this particular methodology we call it fine tuning. Another solution to data size challenge or the problem is data augmentation. We can create more images from a given image by performing certain operation like rotating the image, changing the contrast of the image, or performing zoom operation, flipping the image. So certain type of image techniques we can apply for generating new images. Next comes, once we have trained the models, how do we test those models? So basically, whenever we talk about data set, this data set is consisting of 3 sub data sets. the training, validation, and the testing dataset. Training dataset is responsible for the development or building of the model. The validation dataset, sometimes it's the part of the training process. It is used for tuning the parameters. In the training phase itself, we use this validation dataset for testing it. And then finally, we have a testing dataset that is being used for the performance evaluation of the trained model. How does this trained model performs on the unseen data? So basically, this testing data sub-data set is unseen in the training process. What are the major challenges? The first one is patient data overlap. Second one is how do we annotate or label the ground truth images? How do we create this data set? So creation of data set means along with the image, we should have the corresponding label as well. Whether this particular image belongs to a healthy control or the diseased case. Let's see how do we solve these challenges. The first one is patient data overlap. It means that a particular image is also part of training as well as testing data set. So usually, ideally, we should not have the data from a particular patient in all the data sets. It should belong to only one data set, whether it is in training or validation or testing. As you can see the example here, suppose a patient is wearing a necklace here, and we have put this particular image in training data set. And suppose this particular patient belongs to healthy category. And for the same patient, we have taken another chest X-ray after a certain duration of time. At that time also that patient was wearing a necklace. And this particular image belongs to the COVID-19 category, not the healthy category. And we have put this particular image in the testing dataset. And the healthy image is put in the training dataset. Now, during the training, this model will memorize some of the things which is unusual here. As in the case, it will memorize the necklace as the feature of the normal patient. So now, while testing this model, whether this belongs to normal or the COVID-19 category, but if it is wearing that necklace, the same necklace, this model will detect this chest X-ray as normal. So that's the problem of patient data overlap. And what is the solution? There should be no overlap of patients in different data sets. Ensure to have data from same patient in one set, either in test or validation or training. So the approach being used while constituting the data set is, along with the image ID, we should also assign the patient ID. So once the patient ID is assigned, it is easy to divide these data sets. And it is easy to ensure that there is no patient data overlap among these different data sets. Another point that has to be taken care of while constituting these data sets is, firstly, we should sample the test set, then validation set, and then training set. So from the whole data set, firstly, we should constitute the test data set and take it aside. Then from the remaining data set, we sample the validation set and put it aside. And finally, we have the training data set. The remaining one is considered as the training data set. And what about the ratio of the minority and the majority class? So minority, as I was telling you, the diseased case. So ideally, there should be equal number of images for minority and the majority class. And the same distribution should be there in validation as well as training data set, but usually it doesn't happen. But if we have lesser number of minority class images, we have that solution which we discussed earlier, like the transfer learning, the data sets size challenge. So we can take help of those methodologies to ensure that we have equal ratio of minority and the majority class. Next issue with the testing of the model is ground truth annotation, or assigning the label to the images. Some of the medical modalities are very complex in nature. Since they are complex in nature, there is a difference of opinion among the experts. Let me give you an example of histopathology images. There is always a difference of opinion among the doctors. So, how do we create this labeled data set? Of course, the expertise of these radiologists or the doctors has to be used while creating these data sets. So the idea is the consensus voting. The label for which majority of the experts are voting, that particular label will be assigned to the modality. Another way is we can use different modalities. Suppose a patient is having some kind of cancer. So apart from histopathology images, we can use other modalities like MRIs and chest X-ray, or the CT images, computed tomography images, to check whether this patient is having symptoms of cancer or not. So that is the way we can solve this ground truth annotation problem. And finally, once we have trained the models, we have to evaluate their performance. How accurately these models are performing on an unseen data, the test set. So let's take an example. We have two models, model 1 and model 2, and we have a ground truth on the left hand side. So there are total 10 instances in the test set. Let's consider, suppose they are the X-rays or the MRIs. So 5 each for benign and malignant. Now let's compute the accuracy. What is the accuracy? Accuracy is basically the probability of correct detection. So the model 1 is assigning the negative class to each of the ground truth or the test set images. Still, it is 50% accurate. However, in the case of model 2, it is assigning the positive or the negative class to different test images. Positive means it's a diseased case, negative means it's a healthy patient. Still, the model 2 is 50% accurate. So I would have a question to all of you. Which model is the better one? We can't judge it based on a single parameter, that is accuracy. In my opinion, model 2 is better. At least it is able to distinguish between these two classes. On the other hand, the model 1 is not able to distinguish between these two classes. So the point here is, what I want to highlight here is, accuracy is not the only correct measure for evaluation of the models. There are other measures for evaluation of these trained models. So basically, we draw this matrix where on the left hand side we have the ground truth, like the test image is labeled as positive or negative, and on the right hand side we have the output of the model, like what category this particular model has predicted, whether it is positive or negative. So if a test image or the ground truth image is labeled as positive, positive means it is a diseased case, and the model has also predicted it as positive. So this type of cases are treated as true positive. They were positive and model has also predicted them positive. Similarly, in the case of true negative, the test image is labeled as negative and model has also predicted it as negative. So these particular cases are termed as true negatives. The rest of the other two, where we have contradictory results, like labeled as positive but the model is predicting it as negative, and the opposite case, it is labeled as negative but the model has predicted it positive. The patient didn't have COVID-19 but the model is saying that you have COVID-19 infection. So the idea here is these two parameters, these two numbers should be close to 0. These are nothing but the number of the test images classified in these respective categories. So suppose we had 10 positive and 10 negative test images. So ideally, we should have 10 true positives and 10 true negatives and 0 false negative and 0 false positive. Based on these 4 numbers, we define certain parameters for the performance evaluation. Like the accuracy. So accuracy is nothing but the true positive. As I was telling you, only these 2 numbers are of our interest. So the ratio of true positive plus true negative and the total test size is accuracy. Then we have sensitivity. So sensitivity is basically the ratio of all correctly detected items to all items that should be detected. It means it concerns with the positive cases. Similarly, we have specificity. So specificity is have relevance with the negative cases. And then we have ROC curve. So let's take a simple example where we have 10 ground truth images, 5 of each category, and the model is detecting them positive or negative. So let's make that matrix 4, labeled as positive and detected as positive. So how many are there? 1, 2, 3, and 4. So true positive is 4. What about true negative? Benign as negative? 1, 2, and 3. So 3 are there. And rest are false negative and false positive. So based on these numbers, we can calculate sensitivity and specificity. Ideally, they should be close to 1. Now let's talk about the data sets. The public data sets available for research purposes, specifically in the field of MRI, we have various public data sets. You just have to take permission from the originators of these data sets, and then they will give you the permission for downloading them. And once you have downloaded the data set, you can train your own models, a customized model, and build an application over it. So we have Open Neuro, UK Biobank. Different data sets are proposed for different kind of diseases. Abide, ADNI, BRATS. So there are n number of data sets available for research purposes. Similarly, for the chest X-ray images, we have Chexpert, chest X-ray 14. For histopathology, we have MITOS, BRACHIS, Chemia Path 24. You can apply your own models, build your own models on these data sets, and compare the performance with other models proposed and tested on these data sets. So that's all from my side. Let's summarize what we have discussed, and then we'll have a demonstration on detection of COVID-19 from chest X-ray images. So basically, we discussed about convolutional neural network, what is deep learning, and how convolutional neural network has become popular in recent times and giving very high level of performance in different computer vision tasks. We talked about the training of the models. How do we build models? We need large amount of data to train the models along with the labels. We tried to solve the dataset size challenge with the help of data augmentation techniques and transfer learning methodology of convolutional neural networks. Then how do we test these models? How do we sample the dataset in training, testing, and validation datasets? How do we solve the patient overlap problem, ground truth annotation problem? And in the last, we discussed about the evaluation of the developed model. And we also discussed that accuracy is not the correct measure for evaluation of these models. That's all. Let me share another screen where we will be having a demonstration. So I hope the screen is available to you, the Google Colab screen. Just give me a moment. So for the demonstration purpose, what I have done is I have created a notebook on Google Colab. So I hope you all must be aware of what is Google Colab. It's a cloud-based service from Google, and it provides you certain computing resources for developing and testing your models. So you can develop your own code here, train the model, and then test your model. So basically, I have developed a Python script or a Python notebook for testing of chest X-ray, detection of COVID-19 from the chest X-ray. So basically, we developed a model. We trained a model on a public data set for chest X-ray images, and the trained model I have saved on my drive. So basically, the idea with this Google Colab platform provides you the storage for 24 hours only. So whatever you have stored or uploaded on Google Colab will remain for 24 hours or as long as your session is active. Once after 24 hours, whatever data you have uploaded won't be available to you. So the idea is to mount your Google Drive to the Google Colab. So the Google Drive is a persistent storage and the files will remain whether your session with Google Colab is disconnected. So firstly, this particular script is built on TensorFlow version 1.13. Nowadays, we have TensorFlow version 2.x, but this was developed on a previous version. So I am forcing this notebook to use TensorFlow version 1.13. Firstly, I am installing a library PyDecom for the display of the images. So it says that TensorFlow switches to major versions. You have set 113. This will be interpreted as 1.x. Next, we are importing our drive. So I think it is already mounted. It gives me a message that drive is already mounted at this path. So I can see here on the left hand side, we have this G drive, content and G drive. So in G drive, we have my drive, and in my drive I have a folder called COVID-19, and in COVID-19 model I have already saved a trained model. Due to the limitation of the time, the training of this model takes at least 3-4 hours. So the training portion I won't be able to demonstrate to you. However, once the model is trained, we can draw the inference from this model. We can give the unseen data to this model and see what are the detections by this model. So I just wanted to show you that this model is saved in my Google Drive in a particular folder, and then from that folder I'll access this model. Firstly, we will import some of the libraries like NumPy, TensorFlow. CV2 is for computer vision, that is computer vision library. And then I was saying you that this is my model importing script where I'm providing this path content G drive, my drive, COVID-19, which I just demonstrated to you. And here I have the model. And the model is basically this one, model 8485. So it will load this particular section of the code, will load that model. Let me run it. It will take some time to load that model. It is giving me some error. Let me solve it. So I have terminated the earlier session and I'm executing this code again. So while mounting this drive, it asks you the authentication code, and it has given you the link for authentication code. You have to basically log in from your Google ID, copy this authorization code and put it here. So once you have put this authorization code, it will mount the drive. So mounted at this particular path. Then we'll import the necessary libraries. NumPy is basically a library for numerical calculations. Now we are trying to load this particular model, which we have saved on the Google Drive. So it is basically taking the weights and the parameters from the model. Saving the model means saving the parameters and the weights of the model. It has restored those parameters. Now the task of inference. So basically, I'm reading an image from my drive. These are the test image, and on this particular image X, we will apply, this particular image will be fed to the model and we will get the predictions. So predictions will be in the form of scores. So whichever class will be having the highest score, that particular class will be assigned to this image. Okay, so let's take this particular image, X COVID. This image belongs to COVID category. Let's see the example. So this is the particular chest X-ray image, and the prediction is basically it belongs to COVID-19. You can see the confidence score. The highest score is for COVID-19. That way it is being classified as COVID-19 chest X-ray. Let's take another example. Suppose we are considering a normal image. This is a normal image. So we'll run this particular cell of this code, and now this particular image will be fed to the model. Let's see what score comes. So that's the chest X-ray and that's the prediction. So it's for normal, since the score for the normal category is highest among these three classes. That's why it is being classified as normal category. So that's all from my side. Just a minute. So if you have any queries, please let me know. Any queries? So if not, then let's conclude the session. Yeah. tie on, I mean, during the testing. So usually it doesn't happen. You train the model in that way. If there is a tie, if there is a equal score for multiple classes, that means your model is not trained properly. Yeah, sure. Yes, I mean, yes, nowadays, I mean, publishing a data set itself is a novelty, specifically in the field of medical domain. So, I mean, I mean, if a particular domain is exhausted in your words, so I mean, you can try for some newer problems, and if the data set is not available, you can look into creation of the data sets in that particular domain. It depends on the problem you are addressing. If the medical modality has differentiation due to demographic changes, then definitely it will impact the performance of the model. So maybe the impact of COVID-19 might be different in different demographies. They might have different type of impact on your chest X-ray. So definitely that model has to be trained in a robust manner. See, it's all about what kind of data you provide to the model. Sure. Maybe, I mean, I suggest you can share my email ID to the participants. They can write an email to me if they have certain, suppose after certain time, they have some kind of query in this particular field. They can write an email to me. I'll be happy to reply to those emails. I don't have any issue in that. Thank you. Thank you. Thanks a lot for the invitation, and it's always pleasure to be party to MBM. And I would also request to share the feedback of this session, the participant feedback of the session to me. It definitely helps us to improve our further presentations. So I would request to share the feedback of this particular session. Thank you.